In this video lecture, we are going to learn about the continuum approach. Continuum approach is nothing but a hypothesis that we are using when we are analyzing the fluid systems. So it is having a very great significance when we are going to analyze different fluid systems. So now we know what fluid is. So in the last lecture, we have given an engineering definition of a fluid. So we know what exactly the meaning of fluid is. But in addition to this, we should also understand that what exactly the perspective we have with which we are going to analyze the fluid systems. Now, what is the meaning of this perspective with which we are going to analyze the fluid system? So, we will explain this with the help of example. And this perspective, it will result in defining the properties of fluids. So, properties of fluids, they hold a very important great place in the subject of fluid mechanics. So, what exactly these properties of fluids we have and how we are going to define these properties of fluid, we'll see in this part. So now to define what exactly the meaning of perspective is, so let us consider a container we have. Within this container a gas is present. So as we know, the matter consists of molecules and molecules are in continuous motion. So here we have shown the different number of molecules here. So this number is just a representative number we have. Within this system there are millions and billions of molecules are present within this. But here we have just shown some representative number. Now what we are going to do is, we'll first focus only on individual molecule. So this is the first perspective that we have. So when we are focusing on an individual molecule, and if I want to study its motion, I want to study the motion of a fluid molecule present within this container. Now this fluid molecule, it will have different kind of motions. 3 translational motion it will have and 3 rotational motions it will give. So accordingly, if I want to write the equations of motion to define its behavior, in total we'll have 6 number of equations of motion. So the total number of equations of motion for this individual molecule will be 6. But now when we talk about a fluid system, there are a large number of molecules present. So for each and every individual molecule, we have to write individual equation of motion. And accordingly, for this whole system, whatever the number of equations of motion will get, they are equal to 6 into n. These 6 are the different types of motion we have, and n is the number of molecules present within this system. So accordingly, we can analyze that there are very large number of equations we'll get, and this large number of equations are very difficult to analyze. So even computationally it will take a very huge amount of time, as well as it will take very huge amount of efforts to solve these equations of motion and predict the behavior of fluid within this system. And this kind of approach, it is known as the molecular approach. Now this molecular approach, it stands for what? Individual molecule we are considering, and we are talking about only this molecule within the system, and the same thing we are going to apply to rest of the molecules. The next kind of approach, it is known as microscopic approach. Now what is the meaning of microscopic approach? In microscopic approach, what we are doing is, we are making groups of different molecules, and these different groups, how they are going to behave, we are going to study. So the behavior of different groups of molecule we are going to study in microscopic approach. So this behavior will be a statistical average of their individual behaviors. The third perspective that we can have, it's a macroscopic approach. Now what is the meaning of a macroscopic approach? So now I will not have focus on individual molecule, I will not have focus on some group of molecules, but I will focus on the entire system at a time. So as a whole, I am going to study about this system. This kind of thing, it is known as a macroscopic approach. So these are the 3 different perspectives which we have, with the help of which we can analyze the fluid system, either molecular, microscopic or macroscopic. Now what is the macroscopic approach requires? It requires the fulfillment of continuum. Now what is the meaning of continuum is? So here on a micro level we can see there are voids present between these 2 molecules or different number of molecules. But what continuum approach suggests, it suggests that this medium is continuous. There is no voids or gaps present between the molecules. This is known as a continuum approach. Now with the help of this continuum approach, we will define one of the property which is known as the density, which is denoted by rho. Now what exactly density is, so we all know mass density we can define as mass per unit volume. So to define density, what we'll do is we'll select certain volume here. So this volume we have selected, and whatever the number of molecules within this we have, so we are denoting it by small n, and this n multiplied by mass of individual molecule, it will give you the total mass present within this volume that we have considered. So a unit volume, whatever the mass that is present within this volume, it will give you density. So density will be equal to total mass present within the volume V divided by volume. So it will give you density, which is mass per unit volume. But now what we can consider here is, let us consider in this volume we have only two number of molecules, and as the molecules are in continuous motion, if this molecule it came out because of its vibrations, because of its capability to move out, it has moved out, and now here only a single element, a single molecule remaining inside. Now this n, right from 2 it has reduced to 1, because of which the density will get varied. So this variation, it is not significant, it is not considerable. So when we are going to analyze the fluid mechanics systems, the density is a property which is going to define the system. So this variability we can't use when we are going to analyze the systems. Now what is the alternative, or what exactly we can do to avoid this? So to avoid this, what we are going to do is, the volume that we have decided in the previous case, in that case the number of molecules were very small, and now we should decide the volume so that the number of molecules within that volume should be as large that even though some molecules are going out, the density will not get varied by very large amount. So statistical average will give you some specific value. And how to decide this volume, what exactly the critical volume should be? So it is decided on the basis of two relative parameters. First one is mean free path, second one is characteristic length of a system. Now what is a mean free path? Let us consider again a container we have, different molecules we have. Now mean free path is nothing but what? If this molecule we consider, so as it is in continuous random motion, it will move and it will traverse certain distance, and it will collide with another molecule. So this distance the molecule have traveled before encountering a collision with the another molecule, this distance it is known as mean free path. So this average distance between collisions of two molecules, it is denoted by lambda, and this is known as mean free path. Now what is the second parameter? Characteristic length of a system. Now characteristic length of a system is nothing but what? Let us consider a pipe we have. So I am showing a two-dimensional view of a pipe here. Now along the cross section, what exactly we will have is, the velocity variation will be present like this. So along this cross section, there is a significant variation of velocity present. So characteristic length is nothing but a distance over which there is a significant variation in the property present. So here r can be considered as a characteristic length, but in general we are selecting 2r or diameter as the characteristic length, because only the order is going to get changed, the behavior will not, and this is known as characteristic length of a system. And according to this two relative parameters, one number is defined which is known as Knudsen number. So lambda by L, it is known as Knudsen number. So this lambda, it is a mean free path, and this L, it's a characteristic length. Now let us consider this lambda is larger as compared to the characteristic length. Now because of this lambda by L, in which lambda higher and L is lower, what we will get is the Knudsen value will have to be very large. So when we are having Knudsen number to be very large, the continuum approach is not at all applicable. But when we have this lambda value very small as compared to the characteristic length, Knudsen number will be very small, and hence we can say the continuum approach is applicable. So this lambda by L to be very small, it indicates that the system we are considering, it is having continuous substance, and when it is very large, it tells you that there are considerable gaps present between the two molecules within a system. Now as we understood what exactly the meaning of continuum is, which is nothing but a hypothetical continuous substance, now with the use of this continuum concept, we are going to define the properties of fluid. So now what properties we are going to define? So we have seen about the density. Now let us consider a fluid system. We have a very small element from this we have selected. So this small element, it is exaggerated. So the position of this element, it is signified by x, y, z. This point, it is known as point C. Now within this small element, cubical element, we have selected a point C, and around this, only this portion we have taken. So this is the region we have selected, and these are the different number of molecules present within this region. So whatever the volume we have selected and whatever the number of molecules and their individual masses, all together it will give you the density. Now this volume we have considered as very small volume delta V, and mass of the particles or mass of the molecules present within this, it is given by delta M. Now how we are going to define this density? So density is mass upon volume. So delta M upon delta V, it will give you density. But I want density at this point C. Now how we are going to define that? So it is defined as rho equals to limit delta V tends to x cube delta M divided by delta V. So delta M is the mass, delta V is the volume. Now this limit, what it tells us, so delta V approaching to x cube. So delta V is a very small volume, but it is not tending to 0. It is tending to such a critical volume so that the number of molecules within this volume should be significant, so that there will not be any variation present in the density. So this delta V tending to x cube is a critical volume. Now what is this x? So this x is nothing but a linear distance which is large compared with mean free path. So this x is a value which is greater than lambda. So when we'll have this x value greater than lambda and delta V approaching to this x cube, we can say the density we are defining at a point as limit delta V tends to x cube delta M upon delta V. So this we have defined with the use of continuum